What is problem solving agent? A problem solving agent is an agent that formulates a problem and searches through possible states to find a solution that and finally that achieves a goal. It works mainly in goal based environments where the agent tries to reach a desired goal state. Then basic components of a problem solving agent. A problem solving agent usually includes the following components: that is initial state, state space, actions or operators, transition model, goal test and path cast. First one is initial state. Initial state is nothing but the starting situation of the agent, that is the beginning of the state. The next one is state space. State space means all possible states that can be reached from the initial state. Then actions or operators. Possible actions the agent can perform. Action is nothing but possible actions the agent can perform. Next agent is transition model. It describes how actions change the state from one state to another. The next is goal test. Determines whether the current state is the goal or not. In this state, if the current state is goal state, we can terminate the process. Otherwise, we can continue the process up to the goal state is reached. Path cost. The cost of moving from one state to another. Next, structure of a problem solving agent. The structure or working steps of the problem solving agent are goal formulation, problem formulation, search and execute solution. First, goal formulation. Goal formulation decides what goal needs to be achieved. Here the goal is set. Then problem formulation defines states, actions and goals. The steps to achieve the goals are defined here. Then search. Search means explore possible solutions. Explore each and every node and finally find the goal. Execute solution. Perform the selected actions. Next, simple architecture. Agent operation cycle. Simple architecture involves the following steps. That is, the agent operation cycle involves the following steps: perceive the environment, update internal state, formulate goal, formulate problem, search for solution, execute action. For example, route finding. Finding the shortest path between cities. Here, the following algorithms are used to find the shortest path: breadth first search, depth first search and A-star search algorithm. Okay, then the first state, initial state, city A. Here the goal state is city B. The actions performed here is traveling to neighboring cities. Here we are traveling through the cities. What cities has the least distance? Then path cost, the distance between A and B. Puzzle solving. Examples include 8 puzzle problem and Tower of Hanoi. The agent searches possible moves to reach the goal configuration. Characteristics of problem solving agents: goal oriented, uses search techniques, works in deterministic and fully observable environments, find optimal and feasible solutions. The first one is goal oriented. Goal oriented means the search mainly involves the goal oriented. Here we have to find the goal through various nodes. Next, it uses searching technologies. It uses various searching algorithms like uninformed and uniformed searches, like breadth first search, depth first search, A-star search, like that. It works in the deterministic and fully observable environments. Finally, it finds optimal or feasible solutions. Optimal solution means it is a complete solution. If there is a goal in the solution, then the algorithm or agent surely find the surely find the goal. There is no failure to reach the goal. So only we tell this as optimal solution. Next, advantages of problem solving agents. It can solve complex problems. It can solve the problem flexible and general approach. It can find optimal solutions using searching algorithms. Then limitations. High computational cost. The computational cost is high here. Large state spaces can make searching slow. Large state spaces can make the time. Large state spaces can take more time to reach the goal. It requires good problem formulation. So finally, it is expensive and time consuming process. It uses lot of memory also. Properties of search algorithms. Main properties of search algorithms are completeness. Completeness means it provides 100% solution. If there is a goal in the node means the agent surely find the goal. Then only we can set is at complete algorithm. And one more thing, in completeness means we can visit each and every node without omitting one node. Okay, then finally reach the goal. Optimality. Optimality means the agent surely provides optimum solution. Optimum solution means it provides least path, best path, and it provides best possible solution. It's time complexity. Time complexity means that the time taken to reach the goal. Space complexity means the space occupied by the nodes. Then efficiency. Completeness. Completeness means the algorithm guarantees finding a solution if one exists. If a goal state is there, then the algorithm surely find it. For example, breadth first search is complete when the search space is finite. The next property is optimality. Optimality or optimum solution means the algorithm finds the best or lowest cost solution. It finds the best path as well as lowest cost solution. The path found is the most efficient among all possible paths. This is the least time taking path. Time taking as well as it occupies only less memory also. Example, A star search algorithm can provide optimal solutions with a proper heuristic. Heuristic function means the path cost that used to reach the goal node to start node or node n to the goal node. The complexity, time complexity. Time complexity means how long the algorithm takes to find the solution. The amount of time taken by the algorithm to find the solution. It depends on the number of nodes explored during the search. If the tree has, if the tree is small and it has only limited number of nodes, then the algorithm take only less time. If there is more number of nodes, then we have to visit more number of nodes. So it will take more time also. Here common parameters are branching factor and depth of the goal node. B means branching factor. Branching factor means number of child a parent node have. D means depth of the goal node. Depth means the level of the goal node. Then the formula for the time complexity, O of B power D. Finally, time complexity means it measures how long the algorithm takes to find the solution. It depends on the number of nodes explored during the search. Branching factor here B represents branching factor and D represents depth of the goal node. Branching factor means number of child a parent node have. Depth of the goal node means the level of the search tree. Here the formula for time complexity is O of B power D. Next one is space complexity. It refers to the amount of memory required by the algorithm. It refers to the amount of memory space required by the algorithm. Some algorithms require large memory to store nodes. Some trees has large number of nodes. So in that cases, it requires large number of memory spaces. Example, breadth first search requires high memory because it stores all nodes at each level. Because in breadth first search, we cannot eliminate a single node. We should visit each and every node. So it takes high memory space and high time, more time also. Efficiency. Efficiency describes the overall performance of a search algorithm. Efficiency means performance. Here efficiency describes the overall performance of a search algorithm. It depends on time taken and memory used. Heuristics algorithms improve efficiency. Example, A-star algorithm uses heuristics to search faster. Heuristics means it's a function. We denote it as f of n. It indicates the path cost from root n to goal node. The algorithm chooses least heuristic path to search the goal. So the heuristics uses to search faster. Searching algorithms help an AI agent find solutions to problems. They explore the state space to reach the goal state. They explore each and every node and check whether the current node is goal node or not. If the current node is goal node, then the algorithm is terminated and return the goal node. Otherwise, the search will continue until the goal node is found. These algorithms are important for problem solving agents. Examples include path finding, puzzle solving and game playing. Types of searching algorithms. Searching algorithms are mainly divided into two categories. Uninformed search or blind search, informed search or heuristic search. These methods help agents explore possible solutions in different ways. Uninformed search or blind search. Uninformed search does not use extra domain knowledge about the goal. It explores the search space blindly. It uses only information about the initial state and possible actions. So only here we does not use any extra domain knowledge about the goal, as well as here we don't use the heuristic functions also. So only the search is termed as blind search or uninformed search. The examples for uninformed search are breadth first search, depth first search, uniform cost search, depth limited search, iterative deepening depth first search, and also bidirectional search. Okay. Now let us see about breadth first search. What is breadth first search? BFS is an uninformed search algorithm. So here we don't use any heuristic knowledge and domain knowledge. It explores the nearest nodes first before moving to the deeper nodes. It explores the nodes breadth-wise only. It does not go to depth-wise. So only we termed as breadth first search. It uses a queued data structure for implementation. That is, here we use first in first out feature. It guarantees the shortest path in unweighted graphs. Here we use unweighted graphs. In uniformed cost search algorithm, there may be some weightage for the path. Here we use only unweighted graphs. Characteristics. It explores nodes level by level. It uses queue technology for its implementation. We termed this as a complete algorithm. Complete algorithm means surely it will find the goal if it is. If there is a goal, then this algorithm surely find. So only we termed this as complete algorithm. Because in breadth first search, we visit each and every node. So surely we can find the goal node. Optimal, when the path cost is equal. This algorithm is optimal algorithm. That's why it provides shortest path and easiest path. Breadth first search is the generally breadth first search is the most common search technology for traversing a tree or graph. The algorithm reaches breadthwise in a tree or graph, so it is called breadth first search. BFS algorithm starts searching from the node of the tree and explains all successor nodes at the current level before moving to nodes of the next level. The breadth first search algorithm is an example of a general graph search algorithm. BFS implemented using FIFO queue technique. The working principle are steps. The following steps are followed by the breadth first search algorithm. You start with the initial node or parent node. Add it to the queue. First we have to visit the parent node, and after visiting we have to add it in the queue. Then remove the first node from the queue and expand its neighbors. Here neighbors are childs, and neighbors to the then after visiting the neighbors, then add neighbors to the queue. Repeat until the goal node is found. Here the steps are start with the initial node at parent node. Then after visiting the initial node, add the node to the queue. Then remove the first node from the queue and expand its neighbors. Here neighbors means children of the starting node. Here we visit the nodes as breadthwise only. Then after completing the visit in the neighbor nodes, then add neighbors to the queue. We repeat this process until the goal node is found. This is a simple tree. Here A is the start node or parent node or initial node. Here B and C are child of the node A. D, E are child of B, and F, G are child of C. Here we have to start the search from the starting node, that is A. First we have to visit the A. Then after visiting A, we put the A in the queue, and then child of A should be visited. That is, now we have to visit B and C. So the next nodes B and C are visited. Then B and C are entered in the queue. Now the child of B and C are visited. That is, here we have to visit the nodes D, E, F, G. So here we have to visit D, E, F, G. Here this is the level 0, B, C in level 1, D, E, F, G in level 2. So the depth of the tree is here 3. The traversal order using BFS algorithm is as follows: A, B, C, D, E, F, G. Here visit root node first. As per the rules, we should start our search in the root node. Then visit the successors in level by level in a depthwise manner. BFS queue operation diagram. In step 1, the queue contains only A, that is, it contains only the parent node. In step 2, here we already visit A, then now the queue contains B and C. In step 3, we already visit B, so we remove B from the queue, and in this case D and E are added in the queue. So queue data structure means it follows first in first out manner. So here the nodes which are come first will treat in first priority. Then step 4, here we have to visit C. Here the queue contains D, E, F, G. This shows how BFS expands nodes level by level. The node we have to visit is put into the queue. Already visited nodes are removed from the queue. This is the technique used here. Here is one simple example illustrate BFS algorithm. Here we have a tree. We have a tree of level 3. Here parent node is A. It contains 2 child nodes B and C. Where B node contains further 2 successors, that is D and E. Here we set the E node as goal node. Here the traversal path is first we have to visit A, so we put A. Then we have to visit the first we have to visit level 0 node. In level 0 the parent is only there, so we put A here. Then we have to visit B and C, that is successors of B and C. Successors are parent of B and C, so we put so here we put B and C. Then we have to visit level 3 nodes, that is the child of B node, that is D and E. So here we put D and E. So here the goal node is E, here we visit E. So now in this case the goal node is found. Here the goal node is found at level 2. So here we can stop the algorithm because the whole goal node is found. Next, properties of BFS. This first property is completeness. It is a complete algorithm because it provides 100% solution. If there is a solution, means this algorithm surely provides the goal. So only we call it as complete algorithm. Then optimality. It is a optimal algorithm. Surely it provides a minimum path cost solution for the goal node. Then time complexity. Time complexity formula is capital O of B power D. Then space complexity means capital O of B power D. Time complexity means the time taken to reach the goal node. That is the time taken for a travel from the, that is the time taken for the travel from A to goal node is known as time complexity. Then space complexity. The amount of memory space used by the processor is space complexity. Here B means branching factor. Branching factor means number of child a parent have. Here the parent A has 2 childs, so here the branching factor is 2. So here the time complexity is capital O of 2 power D. D means depth of solution. Depth means number of level of a tree. Here the number of level is 0, 1, 2. So number of level is 2. So here the time complexity Time complexity is capital O of 2 power 2, that is 2 power 2, 2 into 2 equal to 4. Then advantages. These are the advantages of the BFS algorithm. It finds shortest path, it guaranteed to find solution, so only we call it as complete and optimal algorithm. It is easy to implementation. The implementation is very easy, very simple manner. Then disadvantages. Disadvantages are it requires large memory. If the tree contains large nodes, it requires large memory. Slow for very deep trees. In this algorithm, we should not omit any trees, any nodes. So we should visit here. We should visit each and every node. So for deep trees, it will take more time, and it will take more memory. It explores many unnecessary nodes. Here, as I already told, here we should not omit any nodes. We should visit all the nodes by level in a breadthwise manner. So it explores so many unnecessary nodes. So it is a time taking process, as well as memory space also. It will take more memory space also. Applications. The applications are BFS algorithm are path finding in maps. For example, it will use in Google Map concepts. That is where it is used to find the shortest path. Then network broadcasting, then social network analysis, puzzle solving, then AI game search. These are the applications of the BFS algorithm. BFS algorithm means it is an uninformed search algorithm. That is, it does not require any domain knowledge and heuristic function. So only we said it as blind search algorithm. It explores nearest nodes first before moving to the deeper nodes. It explores only depth-wise in level by level. Each and every nodes are visited by this algorithm. It uses queue data structure for its implementation. Also, it guarantees the shortest paths in unweighted graphs. Here we use only unweighted graphs. It explores nodes level by level. It uses queue data structure. It is a complete algorithm because it provides 100% solution. Then it is a optimal algorithm also. Then the next algorithm is depth first search. Depth first search algorithm. Depth first search means here it travels the search space from root node to the deepest node. In breadth first search, we travel in a breadth-wise. We travel here. We travel depth-wise. So only it is named as depth first search. It explores one branch completely before moving to the next. It uses a stack data structure to keep the track of node. That means it uses stack data structure for its implementation. The characteristics of depth first search algorithm are: it explores nodes deeply. It explores nodes deeply rather than explores breadthly. It uses stack, that means lost in first out data structure or recursion for its implementation. This algorithm may not find optimal solution. It requires less memory than BFS because here we does not visit all the nodes. Here we visit the nodes only depth-wise, so it requires only less time and less memory also. Here, if the search tree is large and it has a large number of nodes, then here we may not find. Sometimes we may not find the optimal solution. The working principle of DFS. Here the following steps are followed in the BFS algorithm. Start from the initial node. Or parent node. Go to an unvisited neighbor. Then the algorithm go to unvisited neighbor or child or successors. Repeat this process until no unvisited neighbors remain. If there is a node already visited by S, then we have to backtrack to the previous node. Continue this process until the goal node is formed. The steps, first we have to step this algorithm in initial node or parent node, then go to an unvisited neighbor, repeat until the steps no unvisited neighbors remain. If there is any unvisited neighbors, if there is any visited neighbors, then backtrack to the previous node and check if there is any unvisited neighbors. If there is any unvisited neighbors, then visit them, or otherwise we do backtracking. Continues this process until the goal node is formed. This is an example graph for implementing DFS algorithm. Here A is the parent node. Here the tree has 2 levels, level 0, level 1, level 2. DFS traversal, it starts at node A. Here first we have to visit node A. Then we have to visit the child of node A. Here the child of node A means node B. Then we have to check if there is any unvisited children. Children is there. Yes, here is one node that is called D, is an unvisited node. Then we have to put D. Here in D we are in the dead end, so we have to backtrack to the node B. Now we are in node B. Here we have to check whether any unvisited node is there. Yes, here E is the unvisited node. Then go to the E. Then backtracking. Here E is the dead end. So now we have to perform backtracking. Now we are in node B. Here we have to check if there is any unvisited successors is there. No, here the B has 2 successors, D and E. D and E are already visited by S. So again we have to perform backtracking. Now we are in node A. Here we have to check if there is any unvisited children is there. Yes, here we have to visit only B and the successors. Till now we have not visited the node C. So we have to visit the node C. So here we put C. Then in C we have to check if there is any unvisited child or not. Yes, the C has unvisited child F and G. Here we have to visit F and put the Q in F. Here in F we have to we are in dead end, so we have to perform backtracking. So now after backtracking we are in the level C. Here we have to check if there is any unvisited nodes or any unvisited child of C. Yes, here one unvisited child G is there, so we have to visit G and put G in the stack. Here in G we are in dead end, so we have to perform backtracking. So now we are in position C, that is we are in node C. Here we have to check whether any unvisited node is there. Here is no unvisited child is there, so we have to do again backtracking. This is the traversal order of DFS algorithm. Here we have to travel in depth-wise manner, so only we have to term this as depth-first search algorithm. Here first we traverse deep path first, then if there is any dead end or any visited nodes, then we perform backtracks. Rather than breadthwise, here we travel in deepest paths, that is depthwise. Then DFS stack operation diagram. In step 1, stack contains, we put starting node in stack. Then pop A, visit A, push neighbors C and B. Then we have to visit A. After visiting A, we push the children or neighbors or successors of A, that is C and B, into the stack. Then pop B. Then visit B. After visiting B node, we push the neighbors C, E and D into the stack. In fourth step, pop D. Here we have to pop the D and visit the D node. Then here now the stack contains C and E. In step 5, we have to pop E and visit E. After visiting E, after completing the visiting E, the stack contains only C. That is demonstrate last in first out behavior of DFS stack. That is, here we have to using stack data structure for its implementation. Stack uses last in first out behavior. Properties of DFS. Property completeness. Here we should not guaranteed. So many fail in infinite depth. If the tree has infinite number of nodes, in some cases we may not find the goal node. So we call it as incomplete algorithm. So BFS is a complete algorithm, whereas DFS is a incomplete algorithm. Optimality. Optimality means this algorithm is a non-optimal algorithm because it may not find shortest path. It visits only deepest way, so sometimes it provides a longest path. Next, time complexity. Capital O of B power M is the time complexity, where B is the branching factor. Branching factor means number of child a parent node have. Here branching factor means 2, because here the parent node A has 2 childs only, two children only. Then space, then M equal to maximum depth. Depth means the level of the tree. Here the level is level 0, level 1, level 2. Here the level is only 2. Then this formula for space complexity means big O of B star M. The memory usage low compared to BFS. Because in BFS we have to visit each and every node. So memory space, that algorithm requires a lot of memory space. In DFS we can travel only in a deepest way. So it uses only low memory spaces when compared to BFS. Here the advantages of DFS algorithm are, it requires less memory than BFS. Then the second advantage is, it can find solution in deep trees efficiently. It is easy to implement with recursion. The implementation of the DFS algorithm is simpler and easy. Advantages, it requires less memory than. Disadvantages, it may get stuck in infinite paths. As I already told, in infinite path trees, it may not work properly. It will not guarantee to find the shortest path. So only we can call it as incomplete algorithm and non-optimal algorithm. It can be slow in large or wide graphs. So the time consuming is very high. These are the disadvantages. That is, it may stuck in infinite path. In infinite path tree, this algorithm will not work properly. Then here we should not guarantee to find the shortest path. So it is a non-optimal and incomplete algorithm. It can be slow in large or wider graphs. it can that means it can take more time in large and wider graphs. Applications. It is used in the problem solving, that is 8 queens problem or 8 puzzle problem, then maze traversal, then path finding in games, then web crawling. The following areas use the concept of DFS algorithm: puzzle solving, maze traversal, path finding in games, as well as web crawling. The third algorithm is uniform cost search. This search explores nodes based on lowest path cost. Here we set cost for the path. This algorithm explores nodes based on the lowest path cost. Then only it is a optimal solution. It uses priority queue to select nodes. The first algorithm uses queue algorithm, queue concept to implement the queue data structure to implement the algorithm. Then the second algorithm, DFS, uses a stack data structure for its implementing. Here the uniformed cost search algorithm uses priority queue for its implementation. That is unlike BFS, UCS, that is uniformed cost search algorithm, considers path cost. It mainly works on the basis of path cost. So only we can tell this algorithm as uniform cost search algorithm. It is a here we use it. Here we don't go through in depth manner. Characteristics: uniformed search algorithm. It is a uninformed search algorithm. Uninformed search means it does not use any domain knowledge as well as heuristic function. It always chooses the node with minimum cumulative cost. Then only we can find the path with the lowest cost. It guarantees optimal solution. It provides a least path cost solution. So only we set it as optimal solution or optimal algorithm. Complete if search cost greater than lambda. It is a complete algorithm when the condition when a certain condition satisfies. The condition is step cost less than or step cost greater than or equal to lambda. So here it may complete or it may provide optimal solution. UCS working principle, that is uniformed cost search working principle. Start at the initial node, that is here we are starting the algorithm or searching in the initial node or parent node. Check all neighbors and calculate cumulative cost. Traverse all the neighbors or successors and calculate the cumulative cost. Then select the node with the lowest total cost. Repeat the process until the goal node is reached. Use this example graph. Here the parent node is A. Here the path cost for A to B is 2 and the path cost for A to C is 5. Similarly, the path cost for B to D is 4 and the path cost for B to E is 1. And also the path cost for C to F is 2. Here the start node or parent node is A, the goal node is E. The step cost shown in the parenthesis. That is step cost is known as, here the step cost is known as path cost. Here we travel the nodes based on the path cost. We can travel the nodes through in such a way that which node has the lowest, we can check which node has the lowest path cost. Then we have to travel through through that nodes only. Use this traversal example. Here start at A. Here we have to start the process at here. The cost for the node A is 0. Then only we put cumulative. That's why we put cumulative cost equal to 0. Then add neighbors. Here the neighbors are B and C. Neighbors are here. We can call it as neighbors, successors or children. Here the neighbors are B and C. B and C. Here we have to select B because B has only least amount. So only we select B. Then expand B. B has two children, D and E. Here we select the node E because E has the lowest cost. Then here we set E as the goal. Then now the goal is found. Then because now the goal E is found with cost 3. The traversal here, the traversal is A, B and E. The properties of uniform cost research algorithm. Completeness, yes, if step cost greater than or equal to lambda means it provides complete solution. If the step cost greater than or equal to lambda means this algorithm is working in a complete way. Otherwise it may not provide complete solution. Optimality, yes, it finds lowest cost path solution. So we can set this as optimal solution. Complexity, time complexity means big O of B power 1 plus C star divided by E. Space complexity B power 1 plus C star divided by lambda. Data structure, here we use priority queue. Here B means branching factor, that is branching factor means number of child node a parent node have. C star cost of optimal solution. Lambda means minimum step cost. The advantages of the UCS algorithm are it finds optimal solution, that is it should provide minimum cost path solution. It works with unequal path cost. It complete if step costs are positive. Disadvantages, it can be slow for large state spaces. Because in large state spaces it requires more memory and also it requires more time for its processing. So in large state spaces it can be slow. In high memory usage stores all explored nodes, so it can take high memory spaces. It requires priority queue management. Breadth first search we use queue data structure for its implementation. Depth first search we use stack data structure for its implementation. In UCS algorithm we use priority queue for its implementation. Applications. It is mainly used in route planning in maps, then network routing, puzzle solving with unequal move cost, then resource allocation problems. These are the following areas are used the UCS algorithm. These are the problem solving methods and problem solving algorithms. By using these algorithms we can solve a problem